In today's video, we're going to look at the differentiation rules of equations. We're going to look at constant rule, power rule, constant multiple rule, sum rule, and the difference rule. And then we're going to learn how to do something called the product rule and the quotient rule. And then last but not least, we're going to look at finding higher order derivatives. So the second derivative, derivative of the derivative, and on. So let's start with the constant rule. Say we have the derivative with respect to x of a constant, that's 0. For example, say I have y equals 5. Well, the derivative of y with respect to x would be 0. Derivative of any constant is 0. For our power rule, the derivative of x to the n power is equal to n times x to the n minus 1. So the power moves to the front and the degree is decreased by 1. So if I want to find the derivative of x cubed, I would take the 3 comes to the front and I decrease my power by 1, so 3 minus 1 gives us 2. So derivative of y with respect to x is 3x squared. The constant multiple rule kind of puts these two together. It's the constant times the derivative of the function. So if I take 5x cubed and I want to find its derivative with respect to x, I take 5 times the derivative of 3x squared, which I figured out, x cubed, which I already figured out to be 3x squared. Multiply that together, we get 15x squared. Our sum and difference rule says if I take two polynomials, I'm adding together or subtracting them, it's the derivative of the first polynomial plus or minus the derivative of the second polynomial. For example, I have y is equal to 2x squared plus 3x minus 1. So that would be the derivative of that would be, which when we simplify down, we get 4x plus 3 because anything raised to the 0 power is 1. So that's just 4x plus 3. All right, so let's try a few. We're going to find the derivative of y here with respect to x. So I'm going to use the power rule. So I bring the power to the front and then decrease the power by 1. And then I have 7 times 3x squared plus 2 times 2x plus 0. And then that'll simplify down to 4x cubed minus 21x squared plus 4x. Now sometimes we have to rewrite the equation slightly in order to find the derivative. So here I'm going to rewrite the function before I differentiate. X cubed divided by 3 is the same as 1/3 x cubed, and the same thing with the 1/2. So I can bring that 1/2 constant out, so I can do a constant multiple rule here. And that, after finding the derivative of x cubed and x squared, I therefore can simplify this down. And my answer would be x squared plus x. Here's another one that you have to simplify first before we can do anything. So I'm going to take that, since I have one term on the denominator, I can split it up to each of my numerator terms. So I'm breaking up my fraction. And then simplifying these fractions down. And then again, I don't have a rule with x divided by, 5 divided by x, so I have to change that to negative exponents. So this is actually the function, 1 plus 5x to the negative 1 minus x to the negative 2 is the actual equation I'm going to differentiate using the rules that we learned today. So I'm going to take the derivative of y with respect to x, derivative of a constant is 0, and then 5 times negative 1x to the negative 2, because I decreased the power by 1, and that gives us negative 2x to the negative 3. And then simplifying that down, my final answer is the derivative of y with respect to x in this problem is negative 5x to the negative 2 plus 2x to the negative 3. Now I can't leave it written like this, because in the original problem, there's no negative exponent. So if there's no negative exponents in the original problem, I can't leave my answer with negative exponent. So I have to now get rid of my negative exponents by moving that x to negative 2 to the denominator. And likewise with the x to the negative 3. And that's how you would write your final answer. Okay, and we can now use these shortcut rules to find the equation of a tangent line like we did before with our definition of derivative. It's just going to be much faster. So we're going to find the slope of the tangent line by finding we got to find the derivative at the given point. And once we find the derivative at the given point, we're going to use the point-slope form of the equation, which remember is y minus y1 is equal to m times x minus x1 to find the equation of the tangent line. And then we can find the equation of the tangent line of these problems here. So let's start with f of x is equal to x squared plus 3. So I need to find the derivative. So we're going to differentiate these, which is going to be 2x plus 0. So that's just 2x. Then I'm going to evaluate it at the point I'm of interest, which the x value is negative 1. And I get negative 2. So that tells me the slope of my tangent line at that given point is negative 2. So I know my slope of my tangent line, and I was given the point of tangency. So I'm going to use my point-slope form and find the equation of my tangent line. And then get this y equals. And my equation of my tangent line is y equals negative 2x plus 2. All right, so next we're going to find we're given the equation and we want to find it parallel to the given. So first I need to find my derivative of my equation. So I differentiate that and I get 2x plus 2. But I have a problem. I don't have a point to plug in there like I did before and plug in place of x. But I was given an equation which is parallel. So I have this x plus 2y plus 7 equals 0. Now recall that for parallel lines, the slopes are congruent. They're equal to each other. So I just need to figure out the slope of this equation. So I'm going to rewrite this equation as slope-intercept form by solving for the y. And then whatever number I'm multiplying the x by, that's going to be my slope. So the slope of this line is negative 1/2. So that tells me the slope of my tangent line has to also equal negative 1/2. I'm going to rewrite this so that the negative 1/2 is on the other end. That's kind of messy looking. And so to find my x value for my point of tangency, now I'm going to solve this equation for x because I already know the slope at this point of tangency. So if I'm solving for x, I figure out that x point of tangency is at negative 5/4. So now I found the x value of the point of tangency, so I need to figure out the y value. To find the y value, I'm going to take this solution that we have here and plug that back into my original function, my f of x function, and whatever I get as my result, remember f of x stands for our y, will be the y of this point. So now I got to find my y value of the point of tangency. So substituting in place of every x in my original function, negative 5/4, and then working that out, I figure out that y is equal to 33/16. So now I have a slope and a point of tangency, so I can find my equation of my tangent line by using my point slope formula. And I'm just going to simplify this by distributing the negative 1/2 to everything. And then adding the 33/16 to each side. And I get my equation of my tangent line is y equals negative 1/2 x plus 23/16. And that's another example of how to find the equation of your tangent line. So let's do this one last example. So for A, we need to find a tangent line that is horizontal. Well, recall that horizontal means that your slope is 0. So all horizontal lines have a slope of 0. So that means my derivative of f of x, which is 3x squared plus 2x minus 1, must be equal to 0 because our tangent line is horizontal. So I'm just going to factor this. I'm going to factor by grouping. Then you could do in your guess and check or your box method, whichever way you want to. But I decided to just factor it by grouping. So 3x squared plus 2x minus 1 factors to 3x minus 1 times x plus 1. So it's that each of those factors equal to 0. And I solve. And I have two x values. But the direction said determine all points on the graph for which the tangent line is horizontal. So I found the x value. So now I got to find the y value. To find the y value, I plug in my x value into the original function. So we'll go back to our original function. So substituting in 1/3 in place of every x in f of x and simplifying that down. Let's see, I get negative 32/27. So one point on the graph where the tangent line is horizontal is 1/3 and negative 32/27. Now find the second point. I'm going to replace every x in the original function with negative 1. And I get 0. So the other point where the tangent line is horizontal is at negative 1 and 0. Then for part B, it asked us to find the tangent line that has a slope equal to negative 1. So we already found the equation of our tangent line from part A, which was 3x squared plus 2x minus 1. So this time I'm going to take that derivative and set it equal to negative 1, because the slope of the tangent line slope is negative 1. Remember, derivative at a point is the slope of the tangent line. So I'm going to solve this. And I'm going to factor it by taking out my GCF and set each factor equal to 0, and I also get 2 points here. where x is equal to 0. Or x is equal to negative 2/3. And again, I asked for the point of tangency, so I'm not done. I got to replace, go back to my original function, replace every x with 0, and I get negative 1. So point of tangency where the slope is negative 1 is going to be 0, negative 1. And the other point of tangency, I'm going to replace every x with negative 2/3. And simplifying that down, I end up with negative 5/27. So that's just another extension of what we can do with finding, with our knowledge that the derivative represents the slope of the tangent line at any given point on our graph. Now let's talk about our next rule, which is called the product rule. Okay, we use the product rule. We need to multiply two functions together, and it's just kind of a shortcut of multiplying two functions together. So you take the first function times by the derivative of the second, plus the second function times by the derivative of the first. So here in example A, I'm going to take the derivative of y with respect to x. So my first function, which is x cubed plus x plus 1, and I'm going to times by the derivative of that second function. So I'm going to differentiate this to get 4x cubed plus 2x, plus the second function, copy down, times by the derivative of the first function. So I'm going to differentiate the first function this time. And now it's just algebra. It's messy algebra, but it's algebra. And I just need to do the full method, or just kind of multiply these together. So I distribute the x cubed to every term in the second parentheses. Then I'm going to distribute x to every term in the second parentheses. And then distribute the 1 to every term in the second parentheses. And then plus, now I'm going to multiply the last two set of parentheses together. This time, I'm going to distribute 3x squared to the first term in the first parentheses. Then 3x squared times x squared gives us 3x to the fourth, plus 3x squared. Now distribute the 1 to each term, which just means I copy down that first function again. And now we just have to combine like terms. Now be very, very careful as you're doing this. It's so easy to lose terms or get terms combined or forget a term. So I like to get a different color pen or mark them out as I go to make sure I include all terms. So here I'm just highlighting with different color pens so that I make sure that I'm combining all like terms and I'm not leaving anything out. Okay, it looks like there's only one x cubed term. And then all the rest are just one term each. Okay, so my derivative of y with respect to x is this polynomial. So sometimes you do have to go through a few steps. So I'm going to do the same thing on this one. So again, to find the derivative of y with respect to x, using the product rule, I take the first term and just copy it down as it is. And then multiply by the derivative of the second term, plus the second term copied down, times by the derivative of the first term. Okay, so now I'm distributing the 3x squared, everything in the first parentheses. And then I'm going to distribute the 2x, everything in the third parentheses. And combining my like terms, I get 5x to the fourth plus 3x squared plus 2x. And that's how you find the derivative using your product rule. Okay, sometimes it might not be very obvious in the product rule, so I need to rewrite this as 2x plus 1 times 2x plus 1. And so to differentiate this, I copy down the first function, and then I multiply by the derivative of the second, plus the second function copy down, times by the derivative of the first, which just ends up repeating the same thing here. And so that gives me 4x plus 2 plus 4x plus 2, so that's just 8x plus 4. Now that we know the product rule, let's talk about the quotient rule. The quotient rule is when you take a function divided by another function. Now it's the bottom function times by the derivative of the top minus the top function times by the derivative of the bottom divided by the bottom squared. Now there's a saying that's usually used to say this. It's called, usually say low d high minus high d low over low low. Low d high minus high d low over low low. Low d high minus high d low over low low. And the d just means the derivative. Low d high means low derivative of high. Minus high d low, high times the derivative of low. Over low low just means the bottom squared. All right, so looking at this example, let's find the derivative of y with respect to x. So low means I copy down the bottom. D high means I take the derivative of the top minus high, which copy down the top function. D low means I take the derivative of the bottom equation over the bottom equation squared, low low. Now simplifying. So we get 6x minus 4. Now the hardest thing about this is make sure you're distributing that negative to each of these terms. Notice it's negative 6x minus 15. That's a very common mistake, is not to distribute that negative to every term in that second group of terms. Combining all my like terms, this is my derivative of our a here. Now sometimes we have a mixture, the product rule and quotient rule. So I'm going to do the quotient rule here. So low, so I'm going to copy down the bottom, d high, but here to take the derivative of the top, I got to do the product rule because I have two functions multiplied together. So d high is going to be my product rule. Remember, our product rule is first term times the derivative of the second plus the second term times by the derivative of the first. Okay, I'm running out of room, so let me move this over so I have a little bit easier to work with here. So that was low d high. So now I need to take high minus high d low. So I'm going to copy down the top equation just like it is. Copying all of it down. And then I'm multiplying all of that by the derivative of the bottom. That's d low. And then all of this is over the bottom squared. I'm going to run out of room. Let me make that even smaller. Okay, so now we got a lot of simplifying to do. So I'm going to start with the brackets here, and we're going to just do the full method for those first two terms inside the brackets. And then distributing 1 to the second parentheses just copies it down. And then notice I'm keeping my brackets so I don't lose that multiplying by that negative 1. And now I'm going to take 3x squared times it by x minus 1. Okay, some more simplifying. But let's combine like terms in that second parentheses. So that will give us 2x, and then the x's cancel out and the 1's cancel out. So we'll just get x squared. All right, so I'm going ahead and multiply those together. So I get x to the 5th minus x squared. So I didn't think it would simplify down that much. Minus, and then here I'm going to multiply these together. So I'm going to do it off to the side, and so I can write my answer. So I'm distributing the 3x cubed to each term in that second parentheses inside the brackets. Now I'm going to distribute the negative 3x squared to every term in the second set of parentheses. And then combining my like terms. And sometimes you'll need to go off to the side like this to do some of the algebra, because these can get kind of messy. And then distributing my negative, so I didn't forget my negative sign, all over my denominator squared. All right, ran out of room again. So my final answer, derivative of y with respect to x to this problem, combining all my like terms on the numerator, is negative 2x to the 5th plus 2x squared divided by x cubed minus 1 quantity squared. Whew, okay. Now here's another one that might look a little confusing. We can't do the product rule in this one because we don't know how to deal when we have inside functions. So first I have to rewrite it as a quotient rule. That negative 1 exponent just brings it down the bottom. So I do low, just copy down the bottom, d high, derivative of the top, minus high, just copy down the top, d low, derivative of the bottom, all over low squared, low, low. Okay, now simplifying down with algebra. Now I'm distributing the negative 2x, so make sure you distribute the negative as well as the 2x to each of the terms in the parentheses. Combining my like terms, my final answer is going to be x squared minus 2x minus 1 over x plus 2 quantity squared. That should be a plus sign. Okay, now we're going to look at some notation for the different derivatives. Now we have very many different notations for derivatives. So double for the y prime, this is what the first, second, and the fourth derivative, we don't keep making the tick marks because it gets kind of tedious. And so we start adding just to the nth power. We'll do the same thing for the f of x notation. So here's the third derivative of f of x. The fourth derivative, because it gets kind of tedious making those tick marks, we will write it as f and put the 4 in parentheses of x. And then we do that on until the higher powers of our derivative. Now, it's a little bit different when we do the dy dx notation. So second derivative of y with respect to x looks like this. For our third derivative, we write d3y of dx cubed. And so for our fourth derivative, this is the fourth derivative of y with respect to x. And notice we didn't add the parentheses. And so the same thing goes on forever. So we don't worry about parentheses when we're doing the dy dx notation. And the same thing for the d of dx f of x notation. So here's our second derivative of f of x with respect to x. Here's a third derivative notation for f of x with respect to x. And our fourth derivative of f of x with respect to x. So we do the same thing with the dy dx notation. So our d2dx squared with respect to f of x, that's our notation for the second derivative. Likewise, we do the same thing for the third derivative of f of x with respect to x. And notice we do not add the parentheses again, so the fourth derivative with respect of, or fourth derivative of f of x with respect to x, and the nth derivative of f of x with respect to x. And the big D notation is the same concept. We're just going to add our little exponent there to the degree that this is the second derivative. And then the third derivative of y with respect to x. Fourth derivative of y with respect to x. And the nth derivative of y with respect to x. Now, in order to find your higher order derivatives, you just find each derivative. So the second, the first derivative, those three that I just highlighted, those are the ones I want to use most often in this course. So if I wanted to find the third derivative with respect to x, I first have to find my first derivative, dy dx, by using the rules that we learned today in class, or in this lesson. So my first derivative of y with respect to x is negative 6x squared plus 12x to the negative 4. Then to find my second derivative of y with respect to x, I just differentiate this equation. So I repeat again, and I get negative 12x minus 48x to the negative fifth power. And now the question asks me to find the third derivative of y with respect to x. So I'm going to do it one more time. So I'm differentiating the last answer, and I get negative 12 plus 240x to the negative 6. Now, since this has a negative exponent in the original problem, I can keep this in a negative exponent. So now let's try the fourth derivative of f of x. So first thing I got to do is find the first derivative of f of x, so f prime of x. And then find the second derivative of f of x. That should be negative 60x to the second. And then the third derivative of f of x, negative 120x. And then the fourth derivative. Notice I switched to the parentheses notation with the exponent. Now here I wanted to find the fifth derivative, so I just take my previous answer of the fourth derivative and differentiate that. Remember, the derivative of a constant is 0. Now, this kind of neat thing happens. Notice that I took the fifth derivative of our f of x and I got 0. So what if I kept going? Like maybe if I asked you for the seventh derivative of f of x. So what is the derivative of 0? Well, 0 is a constant. So the derivative of a constant is a 0. And so it just keeps saying 0, 0, 0, 0 once you go past that. So the key, notice that what it switched over is when the power of the derivative is larger than the degree of my polynomial. And this only works with polynomials. If I have like negative exponents, those don't quite follow this rule because the negative exponents keep getting, you keep getting more negative exponents. So here in this example 8, notice that since the order of the derivative, which is 100, is greater than the degree of my polynomial, the derivative, the 100th derivative of 99x to the 99 with respect to x is 0. And I don't have to do all the work in between. I don't have to do that 100 times. Because who wants to find the derivative 100 times? So that's a nice pattern to recognize as you're working through this.